All right, welcome back to the drive-thru. Sponsored as always by the deli. Hungry? Stop by the deli. Make yourself a meatball hoagie on a nice fresh Italian roll with oil and vinegar, oregano, salt, pepper, provolone, toasted. All right, we're getting super abstract here today. We're talking about lines and planes in space. Before we start, I want to remind you that you already know how to find lines in a plane, and it's, very second nature to you. But the one thing that I do want to explain to you is while you are used to calling this equation y equals 2x minus 6, so that's slope-intercept form, you also learned a different way, and that would be point-slope form. So you could call that y minus 9 is 2 times x minus 7, or you could say that it's y plus 6 is 2 times x minus 0, or you could say that it's y plus 10 is 2 times x plus 2, okay? And so now I want you to remember that there were actually more than one way to represent, or one unique way to represent the set of all points that travels in this direction through that point, okay? So one thing we're going to find out is that our equations for lines in space are not unique, okay? Okay, so how are we going to define a line in space? Well, what we need to think about is if we just had, if we knew the point that the line traveled through, okay, and we knew the vector that the line was parallel to, then we could successfully, possibly, define that line as the set of all points that contains a given point that is parallel to a given vector. Okay? So let's say this pink point is just the point x1, comma y1, comma z1. And let's also say this line contains some point x, y, z in addition to that. Okay? And then let's say that this vector that was parallel to the line is just defined by some vector a, b, c. Well, we would know that line, let's call this point P and Q. Okay, line PQ, okay, would be parallel to this vector. Okay, so we do know that. Remember, that's a vector, and we're trying to come up with an equation, and these are two separate things. Okay, but we also know it's parallel to this vector. So we know if we multiply this vector by some constant, it could lead us to that vector. Okay, and that is where they come up with the parametric equation for these lines. Okay, you know that we can define this by a point now and a vector that's parallel to it. So the parametric equations of the line come from the fact that we could equate these things. Okay, so we know that x minus x1 equals at. Okay. or you can just say that x equals x1 plus at. Okay, we know that y minus y1 would have to equal bt. So y equals y1 plus bt. And then similarly, z will equal z1 plus bt. So this is something you've probably never seen before. This is called a set of parametric equations. Okay, the parameter in this case is t. Okay, and this set of parametric equations describes a line in space at a given time t. Okay, so this is the general set of parametric equations for a line in space. Now remember that, because we're also going to be able to write them as a set of symmetric equations. So if we already know that x equals x1 plus at, y equals y1 plus bt, and z equals z1 plus ct, plus ct. Okay, well, this is, if you remember, this t was some constant that we multiplied by that black vector in the on the last page. So that t represents the same t in each one. So if we solved for t in the first one, you get t equals x1, x minus x1 over a. But you also get that t equals y minus y1 over b, and you get t equals z minus z1 over c. So another way to write our parametric equations, which is what I just boxed, that represent the equation of a line in space, would be to set these three things equal to each other simultaneously, and that would be x minus x1 over a equals y minus y1 over b equals z minus z1 over c, and you're probably already getting overwhelmed. So this is totally new stuff. It's harder than you could ever imagine to define a line in a plane. So you might have to pause the video and rewatch it at this point. Okay, but let's see what this tells us. A, B, and C came from the vector that was parallel to our line. So we know that our line is parallel to the vector A, B, C. It's parallel to that one. And we also know that our line contains the point x1, y1, y1, z1. Okay, so that's what we know. Think about how that will be utilized in either of those forms. It's true for both of them. Okay, so now we're going to talk about representing a plane with an equation or a set of equations. Okay, and this is going to be a little magic carpet ride. So how in the world are we going to describe to somebody? First of all, I want you to know that by definition, this plane is going on forever in every direction. And even though it's going on forever in every direction, it's still important that we can represent it and that it can be relatively specific. Okay, so what I want you to envision, and this is going to be hard to draw, is a joystick coming out of this carpet that you could hold and control the carpet with. Okay, so right here is a right angle, and this thing right here, that's our joystick. So if our If our plane looked like this, then our joystick might be facing up. Okay, if our plane looked like this, and we were trying to envision that plane in 3 dimensions, our joystick might be facing, you know, close to what we would consider horizontal. Okay? Now, I know what you're thinking. Well, how come we didn't choose this perpendicular? Okay? Or that perpendicular joystick? Well, as it turns out, if you think about it, it's not going to matter. Those two vectors are parallel to each other. In this case, if we call this x comma y comma z, then we might call the green one minus x comma minus y comma minus z. Okay? So remember, they are referring to parallel vectors. But I want you to imagine that you're riding on a magic carpet. That carpet represents the plane. If you push that joystick forward, your carpet will turn down. Okay? You just moved your carpet down like you're flying the carpet. If you take your joystick and turn it to the right, your carpet just barrel rolled, okay, to the right, and now you're sitting on a carpet whose flat part is completely to the left and horizontal to the sky. We are going to define our plane by a vector orthogonal to it, okay, and a point in the plane. So let me explain this to you the best I possibly can. Okay, imagine you had a vector and you had a vector in a plane that started, let's say, from x comma y comma z and traveled over to x1 comma y1 comma z1. So those are points, okay? Now, imagine you knew that at a certain point you had a vector represented by a comma b comma c that was orthogonal to the red vector. Well, what we want to do is represent the plane as the set of all points. Let's call that n. Let's call that PQ. We want to define this green plane as the set of all points so that n dot PQ equals 0. The set of all points that contain the vector perpendicular, or the vectors, I should say, perpendicular to our joystick, to n. So we could call our n a comma b comma c, and our PQ, we're just going to say x minus x1 comma y minus y1 comma z minus z1, and we want that to equal 0, and that's how we're going to come up with the equation of a plane in space. So this will not be a parametric and will not be a symmetric equation. This is going to look more like the equation of a line, but that should make sense to you because when we were in 2 dimensions, okay, we could represent a line with 2 variables. Now we're in 3. We could represent a line with a singular equation in 2 variables. Well, now we're in 3 dimensions, and it's actually going to be easier to represent this plane because we have 3 variables to work with. So what we can say is we can go from this and we can say a times x minus x1 plus, remember the scalar, the dot product is a scalar, so b times y minus y1 plus c times z minus z1 equals 0. Okay? So this right here is the equation of a plane in 3 space. The general equation. It looks way more similar to, let's say, the equation of a line in standard form. Okay? Alright, so find the symmetric and parametric equations of a line that travels through the points -2. Well, we know we have more points than we need, but we don't have a vector that's perpendicular to it. So let's turn these points into vector AB. Okay, 1 minus a -2 is 3. 3 minus 1 is 2. 5 minus 0 is 5. And we know that this vector AB is parallel to the plane we are trying to define or find the equations for. So, notice, parametric equations. Normally those are easier to come up with. First, we can say x equals -2 x1 plus 3t, y equals 1 plus 2t, and z equals 0 plus 5t. You could also say x equals 1 plus 3t, y equals 3 plus 2t, z equals 5 plus 5t. Both of those would be correct parametric equations for the line that travels through these 2 points. If we wanted to do the symmetric equations, we would solve each one of them for t. Okay, so in this case you'd get x plus 2 over 3 equals y minus 1 over 2 equals z over 5. And this could be a correct symmetric equation. But you can have another correct symmetric equation, and that could be x minus 1 over 3 equals y minus 3 over 2 equals z minus 5 over 5. And believe it or not, both of these 2 circles and both of these 2 boxes both represent the same line in space. Okay? Don't let that freak you out, because you've already been through that before in 2 dimensions. Okay. Find the equation of a plane that contains the following points. So we've got an A, a B, and a C. Well, we know that vector AB will be -2, 3, 0, and we know that vector BC from B to C, -2 minus 0 is -2, 1 minus 4 is -3, 4 minus 1 is +3. So we know that AB and BC are both in this plane. We got we got 2 vectors in this plane, okay? All right, now if we took the cross product of these, that would give us our joystick. So if this was our plane, okay, what we want is a vector that's orthogonal to both, or orthogonal to the plane. So we need to do AB cross BC. You could do it the other way. It doesn't matter. Hopefully you guys understand that. So -2, 3, 0, -2, -3, 3. The cross product is equal to I times 9 minus 0 plus j times negative 6 minus 0 plus k times, I told you, I do it wrong all the time, plus k times, okay, 6 minus negative 6, so that's 12. Okay, so we know that this blue vector there is 9, negative 6, 12. And that is perpendicular to our plane. So to find the equation of the plane, you can use any of those points, any of them. I'll use B because it contains a 0. So I can say x, so let's see, 9 times x minus 0. Remember, the dot product has to equal 0. That's all we're saying. And we're trying to represent all the points in the plane, so we want x minus 0 to represent the first term of some vector in that plane. So 9 times x minus 0 minus 6. Nope, that's going to turn into a positive 6, isn't it? Yes, yes, yes. Oh, that saves me a lot of time having to redo this video. Plus 6 times y minus 4, okay, plus 12 times z minus 1 equals 0. And that is your equation. Now, a lot of times they'll clean it up by distributing. So 9x minus 0 plus 6y minus 24 plus 12z minus 12 equals 0, and then they'll clean it up to look like this. 9x plus 6y plus 12z equals, let's see, you get a negative 24 and positive 36. And that's about enough of that for now. Boom!